Okay, okay, we'll try to get the word problems in one video. We'll see how that goes. Basic curve sketching problem. I think you need to notice, first of all, that this denominator can never be 0. It is x squared plus 9. The lowest number that ever will be is 9. Some of you may factored this somehow and got plus and minus 3's. That's not, or root 3's or whatever. That's not correct. Okay, so this is a nice one, and the denominator is going to be positive on my original guy. There is not going to be any vertical asymptote then, because vertical asymptotes occur when the numerator is 0, which would be at when the numerator is not 0, rather, but the denominator is. And since this denominator is never 0, there are no vertical asymptotes because x squared plus 9 is never equal to 0. To find horizontal asymptotes, again with your original function, and since this is a polynomial, its limit to positive or negative infinity will be the same. For other types of functions, you need to look right to the positive infinity and negative because you might get different horizontals. But this guy is one of our basic rules that says when the degrees are equal, we take the ratio of the leading coefficients, which would be -1 over 1. So this is y equals. Remember, horizontal lines are y equals. A lot of you didn't write that. Y equals -1 is your horizontal asymptote. And limits to infinity, that's what gives you your horizontal asymptote. Okay. Then we want to know increasing. Increasing, decreasing, relative maxes and mins all come off of a sign chart or analyzing the first derivative. Now, your first derivative is given to you. Again, the denominator is never 0. So I don't have any critical numbers of that type, where you'd have a derivative undefined because the denominator was 0. The only thing I've got going on is the numerator could be 0, and therefore the whole derivative. Remember, a fraction 0 only when its numerator is. So negative 18x could be 0 when x equals 0. That's the only value I needed on my sign chart. At 0, this is x and this is f prime of x. At 0, the first derivative is 0. That tells me that wherever the first derivative is positive, I'm going to have increasing, negative, decreasing. To get the sign, all you have to do is plug nothing into the denominator, it's always positive. Put a positive value for x in here. But because of the negative, you get negative. So for any positive value, the first derivative is negative. And for any negative value, minus a negative would be positive, the first derivative is positive. Therefore, the function increases where its derivative is positive, and there's your answer, negative infinity to 0. Also, we ought to be able to see right from this chart, right here, that because f prime changes from positive to negative, plus to minus, that's a relative maximum. Actually, because it's the only sign change, it's an absolute maximum. And we'll need that later on our graph. Okay. All right, second derivative tells us about concavity. Well, our second derivative was given to us. Again, its denominator is always positive because of the x squared plus 9. So this is the only term that could make the fraction 0, so I'll set that equal to 0 and solve. When I do that, I'm going to get x equals plus or minus, that's the square root of 3. Okay, that gives us two values with the second derivative. This was in an area marks second, well, it's about concavity. Concavity is second derivative, but that's a sign chart for the second derivative. So on this sign chart, I put zeros above the values that made it 0, and again, I just plug numbers in. And all I'm plugging numbers into really is just the x squared minus 3 part, because it's the only thing that makes this change signs. So if you think about it, if you plug a 0 in here, then you'd have x squared minus 3 would be a negative number, it'd be -3, you got negative signs. For any number out here like 10, 10 squared minus 3 is positive, and since -10 squared is also 100, -10 squared minus 3 is positive. We get positive signs on the outside, therefore our graph is concave up where we see the positive signs. Negative infinity to negative root 3, and root 3 to infinity. Now this didn't directly up here ask about inflection points, but down in the graph part it did. So you should know that you have inflection points where the second derivative changes signs. So that's going to happen at x equals negative root 3 and x equals positive root 3. Now, as you're thinking about your graph, you're going to draw a graph. If you're going to draw a graph, you need to plot your points in the right areas, so we want some y values here, okay? Now, on my original version, I had an arrow pointing up here that said min 0, 0, which is clearly wrong. It's a max 0, 0. Why did I know it was 0, 0? Because I plugged the 0 from my analysis of the first derivative. That's where our max is. I plugged that in up here, and I got 0 over 9, which is 0. Okay. Also, to get the y values at my inflection points, okay, all you had to do was plug in that root 3 to your second derivative formula. Okay, so what do I have here? I've got the square root of 3 squared over the square root of 3 squared plus 9. And that works out to be a negative out front, sorry, because there was a negative way up here on my original function, okay? And since we were squaring, when I put my negative root 3 in, I got exactly the same answer. And I'm not sure that I wrote that down anywhere. But we get exactly the same thing. If you square a negative root 3, you get a positive 3. But because of the negative out front, it would still be negative. So here are my two inflection points. Here's the area where I'm concave down, and there's my maximum value at 0, 0. Here is the asymptote that they told us to sketch. Labeling the points means putting the points on the graph, but also providing their coordinates, okay? I think I cut you a little slack if you didn't put the coordinate down there. For the y's, provided you were in this range, but some of you had your graph way up here somewhere. Okay. Okay. This was our limit definition of the derivative, and it's at a number a. Okay. Normally, we would write for the limit definition of derivative. If it just said in terms of x, we'd have an x where all of these a's are. But this is at a number a. And if they were asking you to use that to find f prime of 5, if they actually gave you a 5 or any number, you just plug the 5 in for the a's. If they ask for f prime of x, which is a general formula, then you have x's plugged in here. I make a comment on the next page about that. Okay, now it says use the definition in part A. Okay, well, the definition of part A was f prime of a, so I continued with that, which the author did, to find the derivative of f prime of x. You'll see in my note on the next, over here, important C note next page, that I felt like you guys were perfectly valid in saying, since they didn't say to find the derivative f of x at a, they just said the derivative of f of x, I think you were fine to leave x's in there, okay? So it's just a matter of interpreting the question, and I've got it worked out that way on the next page. But this is what the author intended. They intended you to continue with the a bit. So either way, it's the limit as h approaches 0. This is f of a plus h would be what you get when you put an a plus h right there for your x's. You're only squaring that part. And then plus 1 from the plus 1 minus just f of a, 2a squared plus 1, all over h. You want to square this part out. Clearly show your work and don't scribble stuff out because I can't read your work if you do. So this is a plus h squared. You get a squared plus 2ah, don't forget that middle term, plus h squared. If you don't remember that formula, just use FOIL and multiply a plus h times a plus h. Okay, then you get your plus 1, and then I distributed my minus through those parentheses to get this. Now I really did a couple things here. I mentally said, well, that's going to be 2a squared minus a 2a squared, so it was gone. I've got my plus 1 minus a 1, it's gone. So all that was left would be 2 times 2ah, which is 4ah, plus 2 times h squared, which is the 2h squared. Okay, so there's a little work I didn't show, but I think that's probably okay there. Now I divided by h still, but notice now every term has a power of h, so you take one out, and now you're here. Now you can put 0 in for h, and your answer is 4a. If you had x's in your problem, which most of you did, which is fine, then here's the work on the next page for f prime of x. And if they just ask you, they didn't say anything about a's or particular numbers, and they just said find f prime of x, this would be what you do, and it's exactly the same work with the same cancellations. Here I actually multiplied through by the x, so that's the step I didn't show as well on the other page. You see that one, you end up here, you cancel a power of h, and you plug h equals 0 in, and you're done. So if they're saying find the derivative of f of x, and they don't tell you about f of a or anything like that, that's what you want. The other problem on that page was just a nice, I hope simple for you, but some of us are missing this, and this is a very basic first semester concept, that the equation of a tangent line, all you're using is point slope. If you forget point slope or anything like that, the first page of Calculus in a Nutshell has stuff. I'll be darned. Well, it ought to have that. Those are things we've been using all year long. Well, let me just write your point slope. That's something that ought to be on there. Other things on that page, you see all your volumes and area formulas, your area of a trapezoid and a triangle, and all of that good stuff that you're supposed to know going into the test. Absolute value, all of that. So make sure you know that. I will add that and rescan the Calculus in Nutshell first page, I think. So what I want to put on there, by the way, is that equations of lines, and we've used these all year. One is y equals mx plus b. That's m equals slope. B is the y-intercept. That's one of your favorites. And the other is my favorite. Y minus y1 is m times x minus x1, where m is the slope, and x1 comma y1, that's your point. Okay. So we're going to use that second one because we've been given a function, 3x squared. Our derivative of 3x squared by our basic rule is 2 times 3x to the first, or just 6x. That derivative gives us our slope when we plug in x equals 1. So f prime of 1 is 6. We need the y value, though, and that's just f of 1. We get that by plugging 1 into this function. And f of 1 is 3 because f of 1 is 3 times 1 squared. That's our 3. Okay, now we just use our point slope equation that I showed on the previous slide that I put in there. My point is the 1, 3, so it's y minus the y coordinate of the point is the slope times x minus the x coordinate of the point. And we're done. I mean, some of you took it further. If you wanted to, you said y minus 3 equals 6. X minus 1, oops, sorry. I had a side note going into my mind there. By the way, if you did this, y equals 3 plus 6 times x minus 1, that's actually the linearization of this function at x equals 1. That's we can look at our linearization formula, but it's basically just the equation of a tangent line written that way. Or you could have solved this all the way out and got it in slope-intercept, but that was full credit back there. Okay, our next one was so easy it was hard. If we want to have continuity at x equals 0, then the function has to be defined at 0. It is, because of the or equal to, this is its value at 0. Secondly, the right and left-hand limits as x approaches 0 must be the same. Well, that means that if I take the limit from the right side of 0, this is the function I'm taking the limit. The limit as x approaches 0 of x plus k is simply 0 plus k. It's k. And we need that limit to equal the limit from the left side of 0. Well, from the left side of 0, x less than 0, I'm using this definition for the function. So as I approach 0, this becomes 2 minus 0. It becomes 2. So all you have to do is set the two versions of your limit together, and you're going to have your answer. K is 2. Okay, we've got our area between curves problem next. And what we've got here, first of all, you need to have some conception that this is just a parabola opening upward. So you don't have to put your intercepts in, but you see if x is 0, y would be 3, so that's like 0, 3 there. And this is a line. It's y equals mx plus b, but the b is written first. It's negative x plus 5, so that has an intercept of 5, someplace higher than that 3. And it's got a slope of negative 1 because of the negative on the x. So we graph this. Okay, so now what we've got, we need to find the intersection points, because remember, an integral gives us area. And we want the area between these two curves, so we take the top curve, which is the line, minus the bottom curve. We think of having a dx slice there. Okay, so the intersection is found by setting these two equal. We get to here. Now please, when you get to here, you're going to factor. We want two things that multiply together to give us that. Well, you put an x in both of the first spots, because that's how you're going to get your x squared. And now you're just looking for two numbers that multiply to minus 2, but add to a positive 1. They are 2 and negative 1. If you're not sure you got it right, just check using FOIL. X times x is x squared. That's 2x on our inside terms, and minus x on our outside terms is a plus x. And then 2 times negative 1 is negative 2. You've got it. If you set each of these equal to 0, if x plus 2 equals 0, you get x being negative 2. If x minus 1 equals 0, you get x equals 1. Those are your limits. Okay. And now, what are you going to integrate? You're going to integrate the top function, which is the line, minus the bottom function, which is the parabola. Make sure that you simplify this before you do your integration. This simplifies very nicely into this, and now you only have the 3 terms to deal with. Now remember, some of you are still making a mistake here, that when you're integrating, okay, well, let's do the integration step first. That's going to be 2x from the 2, minus x squared over 2, power rule, minus x cubed over 3. And now when you do your evaluation, you always plug the top limit in first, the 1. Some of you are plugging the bottom limit in. Plug the top limit in to your function minus the bottom limit plugged in to that same function. So don't get those messed up. It's going to be top minus bottom again in this concept. Now in this problem, they didn't give you any credit. If you made it to here, that was full credit if you showed that. So I'm not going to waste your time with the fraction work, but it did end up being 4.5. Now, you should go ahead and work it out, because unless they tell you not to simplify it, it's hard to say what you ought to do there. Okay, problem number 16 is this concept of linearization. Earlier, I tried to remind you that a linearization is nothing but the slope, but the equation of the tangent line. Back in this problem, this was the linearization. This was according to the formula there. Let's write the linearization formula up here. This is the linearization at x is equal to the function's value at some value a that you get to choose, plus the derivative at that value you get to choose, times x minus that value that you get to choose. And looking back at the problem we had back here in the concept of linearization, this tangent line is exactly in that form. This is the function's value at 1, which is the value they gave us, we didn't get to choose it, plus the derivative at 1 from this problem back here, times x minus 1. Same formula. Okay, now, we wanted you to show the linearization at the point you chose, and most of you chose, well, if I'm going to approximate this 2.02 cubed, then I'm going to choose 2 because I know that 2 cubed is 8. Okay? And the function that I'm approximating on is the cubing function, and I've chosen my a to be 2, and that gave me the 8. So now we're going to go find the derivative at that point we chose. Show your work, please. This is f prime of x is 3x squared, so f prime of 2 is 3 times 2 squared, which is 12. So here's what I wanted when you're showing your linearization at our chosen point. This is the linearization of x, that's the y in the tangent line, equals the function's value at the point you chose, 2, and we figured out f of 2 was 8, 2 cubed was 8, plus the derivative, which was the 12, the derivative at 2 was 12, times x minus the value you chose. Now to get your approximation, which is the other part, use your linearization to approximate 2.02 cubed. You plug the 2.02 there, and you crank out the answer of 8.24. Okay. Number 17, they would normally not tell you to do L'Hopital's rule. I'm surprised it was. It was an old test. Maybe they had just decided to put L'Hopital in the curriculum or something. But now we should be able to do this without seeing the L'Hopital. Okay? So we've got, this is e to the x minus 1 over sine x as x goes to 0. If you plug a 0 in, you get e to the 0, which is 1, minus 1 is 0. And if you plug a 0 in here, you get the sine of 5 times 0. The sine of 0, that would be the sine of 0, is 0. Now, that's going to be, by L'Hopital's rule, you take the derivative of the top function and the derivative of the bottom function, and then you would try to apply the limit again. And maybe this time you get something. By the way, if you, on the second try, got 0 over 0 or infinity over infinity again, you just try the process again. Okay, now we've got, this is the limit. As x approaches 0, you plug a 0 in there, and e to the 0 is 1. So I've got a 1 up top. And the cosine of 0 is also 1. So this is 1 times 5. You get 1/5 for your answer. On this little limit, we've got the limit as x approaches 3. And I had to put that absolute value bar in there. I forgot that, sorry. Of x minus 3 over absolute x minus 3. Well, you think about this guy for a second. Remember that absolute, just the denominator, that absolute value thing is coming to a sharp point. We're going to have a problem here. Yeah. So here's what you have to do when you're doing absolute value. You have to apply the definition of absolute value. That's on the first page of calculus in a nutshell. The absolute value of any value, a, is equal to itself, a, when a is greater than or equal to 0. But it's the opposite of a when a is less than 0. We used that on another limit earlier, if you'll remember. So what we're going to do then is I have to do this limit from both sides, from the negative side and the positive side, and see if I get the same thing. So the limit as x approaches 3 from the left. Well, if I'm approaching 3 from the left, this is a number like 2 minus 3, that's negative. And the absolute value of any negative quantity is its opposite. So absolute x minus 3 is replaced with the opposite of x minus 3. And now I can cancel my x minus 3's, that's just negative 1. And the limit as you approach anything of a constant is the constant. We redo the limit now from the right side. From the right side, the absolute value of x minus 3, take a number like 4. 4 minus 3 is positive. So this is a positive quantity when you come in from the right. I can replace absolute x minus 3 with plain old x minus 3, and now I get 1 when I cancel. The left and right hand limits are different. As a result, the overall limit does not exist. Okay, problem number, I'm going to go ahead and stop this and do one more video. It's getting long. I don't remember doing a certain problem from the first half that maybe it's not in my pages somewhere. So let me get back to you.